somebody wants it. Somebody wants it, they can have access to it. I am outside, my neighbor's, mowing his lawn. So if you can't hear something, just let me know. But all right. So I am ready when you guys are. What would you like to talk about?
Could we go over when we were doing the ratio aspects of simple harmonic motion again?
Ratio aspects of simple harmonic motion. Sure. What else would you guys like to talk about today?
Can we talk about sorry.
You go ahead.
Can we talk about orbits?
Orbits, sure. Sure, no
Can
problem.
we talk a bit about the lab FRQs?
The lab FRQs, sure.
Can we do a train problem?
A train problem?
Yeah, like the ones with the two blocks being pushed by one force. It was a really long time ago.
Sure. Good idea.
Can we go over analyzing graphs like the slope and displacement and stuff like that?
Can we go over rotational stuff?
That's a pretty big
rotational torque.
Sure.
Can we go over collisions from two different directions, if you know what I'm saying?
Sure. Well, that's a good, healthy list. How about we start with that? And if something didn't make it into your list, then we'll see what kind of time we have after we work through these, okay? I've got a few folks from Mr. Mosser's class joining us today. If you guys are interested, and if you joined on a computer, I can send you a copy of the FRQs my students are working on. They're from my AP, and they're a little bit different than what Mr. Mosser has been kind of giving you. And folks, I'm just going to put it in the chat. And you guys who are from my class, this also includes all the solution guides to them all. At this point, there's no point in keeping any of that a mystery, right? So this is everything. This includes the experimental design. This includes the ones from last week and all the solutions that go with them. So having the solutions doesn't always tell you what you did wrong, but at least it gives you an idea of the kinds of things they are looking for when they are when they're reading through these. And I hope it gives you a kind of an idea of how to improve your writing a little bit so that you can more successfully acquire all of the available points. I need to rearrange something here in my workspace, so if you don't mind, I don't have my normal stuffy stuff everywhere, so I need easy access to my coffee. So, all right, so before we launch into it, let me give you a big reminder. Sometimes the exam isn't about physics. They like to think it is, but it's not. It's about acquiring points. And for you guys who are coming from Mr. Mosser's class, I don't know how much he's talked to you about the test, but I have a few folks that are in my research class and that are in Mr. Mosser's class, and they indicated that they didn't really know the structure of the test as well as they thought they should. It is 45 multiple choice questions. And then afterwards, there are 5 multiple choice questions with 2 answers each. This together is going to be scaled up to 50% of your total score. So the cut scores are kind of important. And we've been talking about this for a while. And to get a passing grade on the exam, you have to make it to the cut score. And they've already decided, or they will be deciding next week, what the cut scores are going to be. And that means you'll already have taken the test. They will decide the cut score based on what they think the test looks like. You can actually pass the test with just your multiple choice, but you've got to get like 35 of them right. That's a pretty high threshold. Multiple choice, generally, I'm happy, and you would probably be happy if you got about 50% of them right. And don't be scared about the 2 answer questions. They are separate from the exam and are located in a different part of the answer key. After that, you have 5 FRQs. And you have 2 12-point and 3 7-points. Now that doesn't, the number of points matters in that this also gets scaled up to be worth 50% of your total. But this is 21 plus 24, so clearly that's 45 total points, and they scale that to 50% of the total number of points. So a point during the FRQs is worth more than a single multiple choice question. When you look at the scale, that's what we have to, it's basically 3 to 2. For every 2 multiple choice questions, I'm sorry, for every 2 FRQ points you earn, it's like getting 3 multiple choice questions right. Now, acquiring points is just as much about knowing the physics as it is about using your vocabulary correctly and ensuring that you answer the question they ask. That's been the biggest takeaway we've talked about, is we answer a question, but we don't give the right kind of support. So in all of these things we're going to talk about, I'm going to try and make a push to also talk about how the multiple choice will be different than the FRQs and how you want to really work on different things to earn the FRQ points. So whoever asked about ratio aspects of simple harmonic motion, I'm not exactly sure what you mean, but I think what you're getting at is something like this. I have a block on a spring. And it has a period of T, so they say T1. I then go and say double the mass. What does that do to the period? What is the new period in terms of T1? So the person who asked about this, is that the kind of question you're wanting me to steer towards?
Yeah.
Okay. So in a question like this, there's several ways to approach it. I favor one more than the other. And the first one is you do need to have a recall of the proper function that describes this. And this is the proper function that describes it. Then you need to recognize that the new function is going to have similar structure to the old, but you're going to have some scaling factors in there. I doubled the mass. So when I doubled the mass, that changed the parameter. We want to find out how the change of that parameter affects the original period. So what I tell my students to do is to look for this function inside their new function, meaning take any of the new numbers that have been introduced and try and separate them from the rest of the function. So if I was to take the long way around that approach, I would probably write the next step looking like this. And this is just for the benefit of people who might feel a little disoriented by dealing with, square roots at 10 in the morning on a Saturday. But I would separate out the square root of 2 from the square root of m over k. And then I would rearrange that so that I have the square root of 2 out front, and then inside I get this 2 pi times the square root of m over k. And that's where I notice that this is my original function, which tells me that t new is going to equal the square root of 2 times the original time. This is most likely going to be the kind of style question you'll see on multiple choice, or it'll be a single one pointer on an FRQ. We've seen it on both. And the goal of this question is less about physics and more about an understanding of how a change in a single variable affects the other variables. So although you brought it forth as a simple harmonic motion problem, the truth is, if you look at your equation sheet, any equation on the equation sheet can be made to serve this type of problem. So, and there's a lot of equations on the equation sheet. So the place that test writers tend to favor with questions like this are things like simple harmonic motion. So we tend to see the period function show up a lot here, both for a spring mass and for a pendulum, because there's a square root in it. The other place we see it quite a bit is gravity. We see it in two ways. We see it in the force of gravity between a couple of objects, but we also see it when talking about the acceleration of gravity. They'll, and just in case you missed this, to find the acceleration of gravity on another planet, you set this equal to ma. You cancel out the m's, and the acceleration of gravity on a planet would be mg over r squared. So we see this kind of question brought up a lot. For example, one way this question would show up with gravity would be the acceleration of gravity on the Earth is g. An astronomer finds a new planet that has twice the mass and 3 times the radius of the Earth. What's the acceleration of gravity on the new planet? Well, the acceleration of gravity on the Earth would be the mass of the Earth times g over the radius of the Earth squared. The acceleration of gravity on my new planet, so g new, is a planet that has a mass that is 2 times the Earth and 3 times its radius. What's the acceleration of gravity on the new planet? So you see how this really isn't a gravity or a simple harmonic motion question. It's about recognizing how they're related to their formula or function. So in this case, I'm going to do the same thing I did before. I'm going to try and separate out the number parts that were added from the original function. So in this case, I get a 2 over 3 squared, but then I have MEG over RE squared here. So all of this is the same. So my G new is 2/9 of the original G. Now, there are faster ways to do this. There are alternatives to doing this too that are different. I prefer this way because to me, it's very clear and it's laid out in an organized manner. But on a test, you have 1 minute and 45 seconds to complete a multiple choice question. And FRQs, you have to be answering them at about a rate of 2 minutes per point earned. You have 90 minutes for 45 points. So I don't think this is a lot, but if it's only going to be worth 1 point, then you've really got to make sure that you're budgeting your time correctly. I believe this is a must get point. Of all the stuff that's on the test, I think it's considered to be relatively straightforward. Multiple choice is the right place for this though, because as you can see, you're going to probably see for the question I just asked, something like answer choice A, 9/2, answer choice B, 3/2, answer choice C, 2/3, answer choice D, 2/9. And you're going to have people who will have gotten all of these answers, especially if they use a ratio and are not particularly adept at doing cross multiplication, which we see quite a bit, where people get something like x equals 4 over y. When asked to solve for y, a lot of students can't do this correctly. They get in a hurry and they think that y equals 4x. And I don't know why students do that, but they do, and that would give you the inverted functions here. So that's why I kind of prefer the substitution method. I think it lays it out in such a way that you really can't inadvertently get the inverse of your answer. Now, I could continue talking about this in regards to simple harmonic motion or something else similar to that if you want me to be a little more detailed about this.
I think you're good. I just needed a recap on how to do it.
Okay. Can I propose something a little different than this too? There is a wrinkle that can be added to something like this that would make this probably more of an FRQ than a multiple choice. You see, I would envision on one of our older honors physics tests, them asking this combined question, saying something like a pendulum oscillates with a period of 1 second on the Earth. What would be its period on the new planet? Now, this would involve both figuring out your new acceleration of gravity and then figuring out how it fits in with the period function. So we just found out what the new acceleration of gravity is, and we have a pendulum that on the Earth has a period of 1 second. We don't know anything about, I mean, we could find stuff out about this pendulum, but that's not really the point of the problem. The point of the problem is to recognize that this equals 2 pi times the root of L over G. We have a new value for G, that's 2/9 G. So T on the new planet is going to be 2 pi times the root of L over 2/9 G. Now, in order to fulfill this one, we have to separate our fraction. I would start by writing that as 9L over 2G to make sure I don't screw up my fraction. And then I'd pull out the number parts, square root of 9 over 2 times 2 pi times the square root of L over G. And this produces that my new period is 3 over the square root of 2 seconds, because all of this was 1. Now, that's a pretty heavy lift for a single multiple choice question. You guys can probably see that, you know, in the way it was structured. And I would hate to think that that would be a multiple choice question, but you can see that it's plausible. You know, would I want to put that on the test? I think it's getting away. Now, the AP Physics 1 test, I think it would favor a question that would ask you first, how is the gravity affected on the new planet? And then maybe would this increase the period or decrease the period of the pendulum? And ask you for a justification as to why. And you would have, go ahead.
Sorry. Why would you do 9L over 2G instead of 2L over 9G?
It was 2 pi times the square root of L over 2/9 G, right? So I multiplied top and bottom of the fraction by 9. And that cancels out the 9 here, giving me 2 pi times the root of 9L over 2G.
Thank you.
So what we've seen in the AP Physics 1 exam has been more like, okay, do the work to figure out what the new value of G is, and then be asked, okay, I have a pendulum that on the Earth oscillates once per second. With my new G, would I expect the period of the pendulum to increase, decrease, or stay the same? And that seems to be what they do on the FRQs. They ask a question that is more about, do you understand how the change in one variable impacts another change? So we know that the G is less. which means that since g is in the denominator and the number got smaller, t has to get bigger. It's going to take longer for it to oscillate. But I also want to remind you, none of that was necessary. If we were told that the planet was twice as massive and 3 times the radius, you could have, without doing any calculation, looked at both relationships, recognized the denominator of this fraction got bigger, so the gravity got smaller. And since the gravity got smaller, that's the restoring force, the time should take longer.
Do you think if they asked this on the FRQ, they would let you like use equations, or that they would say like no equations?
I think a question like this, which is based on some functionally known equations, they would let you use the equations. But I think you would have to explain the functional dependence, right? We've seen that a lot in the answer keys to the FRQs, that you can't just say because of the equation, when R gets bigger, F gets smaller. They want you to, they'll say that you get 1 point for showing that there is a dependence, but then the next point is almost always a point given for telling them, the test grader, what the functional dependence is. So you'd have to say that R is in the denominator so that when R gets bigger, F gets smaller. That's the functional dependence. Does that make sense?
Yes.
All right. Okay, I think we've talked this one into the ground. You ready for another topic? All right, so orbits. I like talking about orbits. That's good stuff. I believe there are about a handful of things you need to know about orbits. And that's why I put that one orbit FRQ on there. When I do the math, and you should think about this for a minute, there are 7 units. One of them is kinematics. That leaves 6 units. 6 units and 5 FRQs, right? One whole unit is called gravity, and that's orbits. So when they dropped out the electronics and waves and all that, they put us in a position where I think it wouldn't be too big of a stretch to expect there to be an FRQ that is maybe attached to or has some information about orbits. So luckily for you guys, the orbit conversation is relatively straightforward in our curriculum. So we're going to break this up into 2 conversations, a specific conversation and a general conversation. So we're going to have the general conversation first. Okay. A general orbit is any pairing of 2 objects, their gravitational force, and some kind of elliptical motion. Basically, it's an object that is trapped inside the gravitational force of another object. Now, I don't want to say this. For elliptical orbits, which is the most general orbit, it's a very non-specific kind of orbit. The object is trapped. It's kind of dancing around the planet. The planet is applying a force of gravity to the satellite. That force is always going to point towards the center. And that force is going to both change the direction of motion of the satellite, but is also going to change the speed of the satellite. So that as the object gets to different places, that force is going to be pointing towards the center of the planet every time. So in this place right here, the force is generally causing a slight slowdown of the velocity, because most of the work done by that force is to change the direction of the planet, of the satellite. But over here, we see that that force is changing its direction, sure, but it's really slowing it down. And eventually the satellite will make it to a location like right here, which is the point where it's furthest away from the planet. When it's furthest away, its velocity is slowest. The force is the least because it's furthest away. So force of gravity is also the smallest. And at this instant, all that force is doing is changing the direction of the object. Now, this next thing is a lot to add to this, but you should know it. The object isn't in circular motion. It's going too slow for that at this moment. It's falling below the circular motion that would cause it to be in a circular orbit. So in the next couple of moments, the object moves to here, velocity this direction. The force is now towards the center. This force is speeding the object up. It's changing its direction, sure, but it's also speeding up the object. Eventually, the object is going to make it here, the point where it's closest. At this moment, the object's velocity is at its greatest. And the force of gravity is at its strongest because it's closest. But at this moment, the object is actually traveling too fast to be in circular motion. So it falls outside of its circular motion, which is what perpetuates this ellipse and keeps it from being in a circle. So when it's here, it's going too fast to be in circular motion. Here, it's going too slow to be in circular motion. That's an elliptical orbit. There's two things about elliptical orbits that I think you should know. The first, whatever's causing the orbit is at one of the focuses of the ellipse. That's a Kepler's rule. The second thing you should know is that there's no external force here. So energy and momentum are conserved. Now, when it comes to any kind of reasonable calculation, I don't think you have anything to worry about when it comes to an orbit that's elliptical. I think you should know that it's at its fastest here at the one side. And I think you should know that it's slowest here. And I think you should know that it's too fast to be in circular motion on this side and too slow to be in circular motion on that side. And yes, I do think it's probably appropriate that you understand that momentum and energy are conserved, but the specifics of that are unlikely to be on the test since it's not really part of our curriculum. Now, it is plausible that you could be asked about momentum here, and momentum is L times W, right? For the, well, not L, I'm sorry, I times W. That's for angular momentum. So when I said momentum there, I meant angular momentum, sorry. Now, the satellite is a point mass, and these V's refer to its linear velocity. So we could write this as mr squared for a point mass times omega over r to get the linear velocity. And what this gives us is the angular momentum of a point mass, r, m, well, I screwed that up. It's v over r, not omega over r. Gives you r m v for the angular momentum. Now, if you look closely at that, you'll notice that when we're over by the closest to the sun, it's RMV when we're close. And when we're far away, it's RMV as well. Since M doesn't change, when R gets bigger, V has to get smaller. That's why it's slowest over here, because R is biggest. It is a perfect inverse relationship. That is something they could ask about. And I know we didn't talk about that very much because it's really never come up. But it is plausible, since we do cover angular momentum and we do cover orbits, they could combine those two topics together. This is an AP Physics C topic. We would have done this already in class. But it's not really as much in our curriculum, so I don't expect it. I expect them, if they're going to talk about elliptical orbits, they're going to talk about them in a general way. And then we talk about the special case. And the special case is a circular orbit. And circular orbits, there are many things you should know about. So any questions about the elliptical orbit stuff? All right, then let's talk about circular orbits, because I do think circular orbits are something that you should have more capacity to deal with. So I'm gonna kind of get rid of all, let's just do a new picture. That'll be easiest. So let's go back to having my thing in the middle and my thing rotate around the edge. A circular orbit is a special case. And I don't think I have to go into too much detail as to why it's a special case, but you should know from math that a circle is an ellipse. So it's an ellipse where the two focus overlap. So it's a special kind of ellipse. For us, when it comes to dealing with orbits, an circular orbit is a perfect pairing of an unbalanced force and centripetal acceleration. It is when the gravitational force between two objects is balanced perfectly by the needs of a centripetal acceleration. So the mass of the object at the center times the mass of the satellite times g divided by the separation distance squared. That is balanced by the mass of the satellite times its velocity divided by the radius. Now I'm careful to use different words here, and you should be too. These are not necessarily the same thing. You should ask yourself, in the case of your problem, whether they are or aren't. Because you could get easily tricked by this. And if I was writing a test, this might be one of those follow-up questions I ask, you know, at the end of the FRQ, where you're saying, well, what would happen if? So I want to remind you that this is the separation distance. That is the separation distance of the two centers of mass. This is the radius of curvature in this case of the satellite. I'm bringing this up because they're only the same number if this object is very small compared to this object, meaning the mass of the satellite has to be much smaller than the mass at the center. This is not true for the moon and the Earth. We might think the moon is small, but no, they're not. These two R's are not the same between the Earth and moon. they're the same, or really close to the same between the Earth and Sun, and they're very close to the same between like a communication satellite and the Earth. In that case, we can say they're the same. But like I said, the end of an FRQ, when I want to see if you're really paying attention, yeah, that's exactly what I would ask about. The first thing I would do is I would say, what happens if the center of mass is here between the two things? How does that affect the problem? And it does have an effect. And so we're going to talk about the base problem real quick, and then we'll talk about this effect. The base problem is really straightforward. When I say base problem, there's only a few things they're going to ask you about here. And if it's a calculation or even a discussion, it's going to center around this relationship first. Now, one of the things that should be pointed out here is you can figure out how fast you're going, or how fast you need to go to be in circular motion. And that's the first thing I would expect you to see here, and the first thing I would expect you to do. Cancel out the M's, cancel out one of the R's, and solve for V. And we find that the V for a circular orbit first has nothing to do with the mass of the object and only has to do with where that orbit is. I'll point out something very important. The further away an object is, the slower it has to go. That's our functional dependence. It makes a bigger circle, but it's going to go around slower because gravity is less. So as you get further away, less pull from gravity, so you don't have to go as fast. Now, you know from our discussion in class that the next thing I'm interested in you guys being able to do is talk about period. And this is where there's something you need to memorize that you have to bring with you to the exam because it's not on the equation sheet. I don't think it's a lot to ask, but the period is the circumference divided by the velocity. And we talked about that a while ago. Actually, we talked about it like this. We said the velocity was the circumference divided by the period. That if you want to know how long it takes to go around something and you know how fast you're going, well, distance over time. But what this does tell you, I hope, is that you could take this, put it here, and get an expression for the period. Now, for all of you people who are going to watch me do math and get upset that I'm going to do it without, all the steps, I'm going to be kind and do this in a couple of steps. I'm going to make this one of the steps. And that's purely so I can do I can just invert that, put it over there. And now, because I have an R inside the radical and an R outside the radical, I'm going to combine them. And you get R cubed in here. Now, two things I want you to see. First, do you notice this looks like some other periods that we've seen before? I mean, I don't know if you see it, but 2 pi times the square root of L over G, or 2 pi times the square root of M over K. Periods all have this look to them. And it's not an accident. There's a circle involved even with simple harmonic motion. Also, it doesn't look like it, but remember gravity was mg over r squared. Now, this is just because I like to make sure everybody understands that there's something magical here. If you rewrite this, you can rewrite this as r over mg over r squared. I'm doing that because the top part is how far away the object is. The bottom part is the force of gravity. You might not know why I'm saying that, but this is a remnant of mr squared, the moment of inertia of a point mass. If I put the m here and an m here, you'll notice I get the force of gravity in the denominator. Remember, all periods, all of them, is inertia divided by restoring force. So we get inertia divided by restoring force even in an orbit. Doesn't look like it, but it's there all the same. So if they tell you, you want to make some conjecture, always go back to inertia and force. It tends to serve you pretty well. So going back to an orbit, that is the orbit equation. There's two of them. There's the velocity of the orbit and the period of the orbit. If I was writing an AP exam and I wanted to bring in some of the experimental design stuff, I would say a student looks on the internet and finds this equation that describes the period of a planet. So the student looks at data from several different moons and clocks their period. What two quantities would they have to graph in order to get a straight line whose slope could be the mass of the planet? Does that sound like something that we've heard in our tests before? For an orbit equation, that'd be graphing period squared versus radius cubed. The reason why that's worth knowing is that's actually one of Kepler's laws about planetary motion, is that this ratio of the period squared to the radius cubed is something he discovered mathematically before there was any Newton's laws or anything like that. And believe it or not, you can look at the 4 moons that circle Jupiter in a telescope, and you can calculate Jupiter's mass by that formula. In fact, that's how it was calculated the first time. Before we really had an idea of the mass of the Earth, we had an idea of the mass of Jupiter. That's not exactly true historically, but it was easier to measure. Now, that's a lot about circular orbits. And it's everything we talked about in class, but that was months ago. I do think we should throw a little bit of a wrinkle in here now. But are there questions to this point? Because I threw a lot at you there.
I had a question about why did you cube R?
When did I?
No, why did you do it?
Originally, there was the R here, like that, remember? Sophia, do you remember that?
Yeah.
So to put it inside the radical, I squared it first. So I put an R squared inside the radical. And then I had an R times R squared, and that made it R cubed.
Okay.
So I think the big takeaway with orbits is you have to have this understanding that it's just a centripetal motion problem that uses gravity for the unbalanced force. But because we have this reciprocating motion of the planet around the satellite around the planet, you can bring in period too, in a way that we tend to not think about it for circular motion problems. Now, we use it to learn how to calculate big numbers on our calculator, but as you've seen, that's really not the way in which the AP exam is going to deal with your calculator. You're not going to get stuff like that. Now, outside of all of this, I need to address the thing I was going to come back to, and that is what about center of mass? That plays a role here. And it's one that I want to make sure we've at least considered. When the two objects don't have the criteria that one object is much bigger than the other. And that's a lot of things. Earth-Moon system is a great example of it. When that's the case, this R is going to be different than the R for gravity. Put a little C there to say radius of curvature. This R squared is still the separation distance, but that's no longer the radius, because objects that are like just floating around in space and don't have a fixed pivot point, they rotate about their center of mass, which is a place between the two objects. Now, we talked about center of mass, but it's been a long time and we don't spend a lot of time on it. Center of mass is a location. It's a place. For two objects, it's somewhere between them. The more equal the mass is, the more it's in the middle. The only thing that you have to know is that when we're dealing with an object whose mass is not much, bigger than the other, this is the radius of curvature, but this is the separation distance for gravity. Now, if we think what that means in the big picture, the force of gravity isn't any different, but the radius of curvature is smaller because it lies in between. So your object actually has to go slower.
Look at that. If you look at this fraction, sorry, you lost me for a minute. My headset died. But if you look at this fraction, you'll notice that since radius is on the bottom, if the left side is a constant, for the right side to match it, the top of the fraction has to get smaller, just like the bottom of the fraction gets smaller. So an object that is not, super small compared to the objects rotating actually rotates at a slower speed. That also means it takes longer to go around because it's going slower. Okay, so give me just a second. I'm going to pause this for a minute. I need to change my
Longer with that, mostly because of the other stuff you guys have asked about. This is the one that's probably going to be the biggest surprise if it shows up on the exam. So let's take a look at that list again. Lab FRQs, train problem, analyzing graphs. Okay, I'm going to do this a little out of order. I want to talk about the train problem real quick because I don't think it'll take long. And also, I thought of something that would be an interesting question if they asked it on the exam, and it was because of something we did yesterday. So train problems, if you'll recall, are just really Newton's third law questions. They generally involve, a couple of objects that are connected by some coupling, so let's have just a couple boxes. Okay, so a couple of objects being pulled by a string. Let's say this is string C, this is string B, and this is string A. Let's say this is M, and this is 3M, and this is 2M. All right. Now, the first question I would ask is, which of these strings has the most tension in it? A, B, or C? Now, I know you guys don't want to speak up because, you don't want to be wrong. But if that's the multiple choice question, you need to speak up. So just send me a direct message. Which one do you think it is? A, B, or C? Let's see if we can think it through. got about 10 people have kind of sent me something here, and not quite equally split, but pretty equally split between B and C. And it's kind of what I expected. I figured no one would say A, but I think that you're being fooled, some of you. And I want to be really clear. C has to pull all the boxes. So it's got to be C. C doesn't know that there's a 2M box, a 3M box, and an M box. C has to pull 6M worth of boxes. B has to pull 4M worth of boxes, and A has to pull M worth of boxes. So when we look at the tensions here, we tend to think that we're only dealing with what's directly connected to the string itself. That's not true. And although string B doesn't pull on box M, there is a tension that's in this direction on the 3M box that occurs because of box M. Just like there's a tension on the 2M box that occurs because of box 3M, and consequently because of box M. In fact, from the standpoint of C, it's just one big box behind it, an entire system of mass 6M. And by the way, this would be still the same answer, even if there was friction involved here. You'll notice I never said anything about friction. I didn't even say if the boxes were moving. As long as the coefficient of friction is the same for all the boxes, and notice I gave a because. You heard that phrase, right? Because, make sure you understand, if the coefficient of friction wasn't the same, that doesn't really affect the answer, but it would be a more complicated explanation. C would still have to pull the most. But ultimately, you can start this problem by just considering the system. The net force in the system equals 6MA for the system. This is tension C has to equal 6MA, Newton's second law. So the acceleration of my system is the tension in C divided by 6M. What makes train problems solvable is that all three of these boxes have to have the same acceleration. They're all connected. So I could consider the net force on box B. There's two forces acting on box B. There's tension B and there's tension A. And that has to equal 3MA. There's also the net force on box A, which is just tension A, and that has to equal MA. But if you look carefully, A is tension C over 6M, and A is tension C over 6M. M's cancel here, and I get that tension A is 1/6 of tension C. Well, sure, it's 1/6 of the entire mass. I bet tension B is going to be 4/6. I have a hunch. So let's see if my hunch is right. Looking at tension B, I can plug in tension A. So tension B minus tension C over 6 equals 3/6 tension C. Looks like when I add that to the other side, I'm going to get 4/6. Now, that's a basic train problem where we have gone and used Newton's laws to show how the force in those cables is related to the masses that they are pulling. But in every case, the tension in the cable pulls with the force necessary to move all of the inertia behind it. I see a clear multiple choice question here. One that asks which of the tensions are the greatest and which is the smallest. In fact, this question has been on the AP Physics C exam before. No reason why it couldn't be on the AP Physics B exam. Now, I would like to ask a somewhat similar question, but for the person who asked about train questions, would you like me to go on and do more with the train question?
I was just curious about this one question on one of the multiple choice tests you gave us. It seemed like an easy point. I just forgot how to do it. It was where two boxes were touching each other, and one was mass M and one was mass 2M. And a force was being applied to the one of mass M. So it was pushing both of them. And it gave like the value of the normal force that the box that mass M was applying on the box of 2M. And it asked what the force being applied to both of them was. And I just couldn't figure it out.
Okay. So again, similar to the train problem, which box had the force applied to it?
The smaller one.
Like so. And they gave some normal force here, N, and they
Yeah.
said that this was M and this is 2M.
Yeah.
So basically we want this force in terms of N. And again, the same thing has to be true here. The force that pushes on the 2M box is this normal force, the normal force between the boxes. So if I was to draw a free body diagram on the 2M box, there'd be a normal force in this direction. I'm not doing the up and down forces, I'm just doing the sideways forces. But if I was to draw the forces acting on the M box, there'd be the applied force in this direction and N in this direction. N is a third law force, so it acts to the right on the 2M box and to the left on the M box. But still, the acceleration of both boxes has to be the same. If M accelerates more than 2M, then M is going into 2M, like inside it. And if 2M is accelerating more than M, then they're separating. So we assume the acceleration has to be the same for, the acceleration has to be the same for both. So a quick look at that is that N equals 2MA. And F minus N equals MA. Good so far? Now, here's the thing. I could do substitution here to get rid of N. And I'd find that the force equals 3MA. That's what we did in the prior problem. The acceleration of the system is based on the mass of all three boxes. But your question, Rylan, was not about eliminating the normal force. It was about eliminating MA. It was getting F in terms of N. So your question is a little bit different. Let's eliminate MA. I can solve this for MA, and I get N over 2 equals MA. So my force minus N equals N over 2. I'm putting this in for MA. So add N to both sides. And I get F equals 3/2 n. Now, interesting side note here. If you look at that result, you find that n equals 2/3 of the force. Now, I'm bringing this up because you applied a force to 2 boxes. 2/3 of it went to pushing this box. That means 1/3 of it went to pushing this box. When you push on a row of boxes, you're dividing the force up. Little bits of that force are being used to move each of the objects. That's not really what's happening, but it's mathematically what's happening. So if I look at the net force on the first box, I'm going to get F minus 2/3, which is 1/3. If we went back to the other train problem we did, same thing was happening here. The tensions in all those cables took the total force, TC, and divided it up amongst the other cables. So 1/6 of it for the last box, 4/6 of it for the middle box. And it doesn't get divided up unevenly, it gets divided up by how much mass there has to be. So let me give you a problem that I think would fool you. It's not a math problem, but I think it's a problem that would fool some of you. It's been fooling everybody all week. So, and you may or may not know what I'm about to do here. If you've been following the stuff with the Atwood machine and the demo I did in class the other day, you might be able to predict what this question is going to be. I'm holding the boxes. And I have to hold them with a tension to keep them in place. Now, if I lower the boxes at a constant speed, does that make T2 increase, decrease, or stay the same? I'd be happy to hear what you have to say in the chat if you don't want to say it out loud. Again, if I'm just holding the 2 boxes and I start lowering them at a constant speed, does the tension in the middle increase, decrease, or stay the same? All right. Got about a 50-50 split. So no one said increase, but which I think is good. And again, this is because we jump to conclusions. Look, everybody, you really need to hear me this time. If you're here for this, and there's a lot of you here, 20 of you here, this is when you made your decision and you typed it in the box and you sent it to me. Did you do that by considering a known physics principle first? Or did you just go with your gut? Your gut's going to get you wrong here. If you can't back it up with a known physics principle, if you can't justify it using a physics principle, then you have no justification. We're traveling at a constant speed. Net force equals 0. Tension didn't change. The tension has to be what it was before it was moving. because the net force is 0. So that's the first thing I need you to remember, is if you can't back it up with a physics principle, with something that was created by somebody that was smarter than all of us, then probably your gut's not going to be the right way to go. Now, I'm going to add to that, because you know that there's a lot of ways this problem can now go. I can say, what if it accelerates downwards? Does that increase or decrease the lower tension? And hopefully now, because I've just exploited you, when I say it accelerates downwards, the only way the bottom box can accelerate downwards is if the net force is now downwards. The only way the net force can be downwards is if T2 is less than 3 mg. Because it's not like 3 mg is changing. The weight of the box doesn't change. But for it to accelerate downwards, whatever is pulling it up has to be less than what's pulling it down. But I think you will get this wrong on the exam. I mean, I just demonstrated that 50% of you would have gotten it wrong. You don't know that because you don't know what people said, but I'm looking at it. And everybody in here knows the ones who said decreases versus stays the same. You know, it's about acceleration, not motion. Now, here's the flip side of that question. And for all of you who remember way back in October, this is the elevator question, where we talk about, you know, what does it take to lift an elevator up to the next floor? So you have to increase the tension in order to get the elevator moving. And then the tension stays constant while it's moving at a constant speed. But then to stop the elevator, you don't pull down on it. You just lower the tension and let the weight stop the object. It's a good question for an AP exam, especially at the end of the year. But what does it look like when I kind of flip the script on it and have so imagine I have like a forklift and it's got these 2 boxes on it, like so. There's a normal force here pushing upwards on the red box and downwards on the green box. We good so far? So do you also see that if I lower the forklift at a constant speed, the normal force won't change? But if I accelerate the forklift downwards, the normal force does have to change. You guys see that? I can only see the faces of like 3 people, so it's hard to know. But I'm going to say, yeah. Now, this has a limiting factor. The tension one did too, but it's harder to see it here. It's possible to lower the forklift too fast, and this box will separate. The truth is, both of them would separate if they're just resting on the forklift. It's a threshold problem. The same problem existed here. You can accelerate downwards fast enough where the tension here becomes 0. And that threshold is G. If you accelerate at G, N goes to 0. Can accelerate it faster than that because gravity is what's actually pulling the boxes down. But it's possible for the forklift, because it's being activated by motors, to go down faster than G. But it's not possible for the boxes to do so. So if you push the forklift down faster than G, the 2 boxes separate from the forklift and from each other. That's a threshold where the normal force would go to 0. And that's a possibility in these train problems to have limiting factors. There's two such limiting factors. That's one of them. When the tension or the normal force could go to zero, and generally that's done when the acceleration is smaller than tolerance or greater than tolerance. The other one that has a factor, sometimes there'll be a limit that a tension can't be any greater than some value. Like the cable will bust if you 400 newtons. So you better stay below 400 newtons. Those are just limiting factors. All right. I think that's pretty good for the train problem. I think we should look at those experimental FRQs now. I think that's on the list, right? We looked at a couple of them already. So let me see. Oh, and analyzing graphs is in there too. It's a lot here. So when it comes to the experimental FRQs, let me see. We talked about this one in class, so I don't really want to go into it too much. This is the one where you're just going to lift the book, measure the angle. Let's see, I may talk about that. Oh, I opened up the wrong one. Let's keep going. Where's question 2? Is there a question? Let me get just the questions. There, just the questions. This is on the second year of the AP Physics 1 exam. This is an actual question that was given. So now it's part of our, we can just kind of give it out. Actually, 2 of these were actually on the original AP exams. And this is the one I remember the most. So the new kind of toy ball is advertised to bounce perfectly elastically off hard surfaces. The student suspects, however, that no collision can be perfectly elastic. The student hypothesizes that the collision is very close to being perfectly elastic for low-speed collisions, but that they deviate more and more from being perfectly elastic. Design an experiment to test the student's hypothesis about collisions of the ball with a hard surface. The student has equipment that would usually be found in a physics laboratory. What quantities would be measured, what equipment would be used for the measurements, and how would the equipment be used? Describe the procedure to use test hypothesis, blah, 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 blah. There's only one way to do this lab. It seems like there's a lot, but if you think about it, what are your real options? You need something that you can bounce the ball off of that's not going to move. What's a likely place that you bounce the ball off that's not going to move? Yeah, I'm thinking the floor or a wall. But if you want to measure something, it might be easier to bounce it off the floor than a wall. And it's just for the simple fact that if you drop it from a fixed height, then you can determine how fast it hits the ground. So the general form of that question is, you need to find something as a student that is a way you can take a measurement and then analyze the data. So this particular problem suggests that you understand that a dropped object from a fixed height will have a velocity when it reaches the ground that is predictable, right? mgh equals 1/2 mv squared. And then the ball is going to bounce off the ground and come back to a final height. So we'll have an initial height and a final height. We don't ever have to actually measure the velocity. We can say that mgh1 is going to be equal to 1/2 mv1 squared, or I guess I for initial. And then when it recoils, 1/2 mv final squared will reach mghf. So it sounds like a collision problem, but it's really not. It's an energy problem. And it looks like you can do this entire lab with a meter stick. So as an experimental design problem goes, I want to remind you ultimately that your job is to find something that you can measure. And I don't mean generic you. I mean you, Megan, and you, Tyler, and you, person that is sitting on the other end of this screen. If you don't know how to take the measurement, you can't write a convincing argument about how to do the lab. Do you follow what I'm saying? The only way you're going to get these points is if you come up with something you personally can do. I've read a lot of your work in this regard, and it is so easy to smell the person who's never held a stopwatch, that just sat there at the lab and wrote the numbers down while somebody else did all the work. If you want these points, you have to be the person holding the stopwatch, holding the meter stick, making the measurement. That's the only way you're convincing. But you also have to have enough of a creative sense to come up with what you would measure. And then for them to turn this into a problem, they're going to ask what you would analyze, what data would you look at, and what would you do with responses that don't seem to make sense? Like, what happens if you get HF is greater than HI? Does that seem like a reasonable possibility? So you would have to come up with, and they talk about this in the question, what happens if you do get that as an answer? Well, it probably means you didn't drop the ball, you probably threw it down. You gave it some energy that wasn't supposed to be there. So you can't come up with like, well, I think that the ground pushed up harder on the ball. What? Earth doesn't do that usually. You need to have something better. So the experimental design questions, they're all going to come down to, like I said, you can do almost every lab with a meter stick, stopwatch, and a scale. Don't make it fancy. You won't be happy with the results. Make it easy. Make it easy. Since I posted all the answers to the experimental design and gave them out to you, I really don't want to spend much more time on it, but there's some stuff here I think we probably should talk about. And I think this is probably not unreasonable, but when it comes to analyzing graphs, I would argue that you have probably 4 that are really, really important that you'd be able to analyze. And the first one, I don't want to spend any time on it because it's so old. You know, it's the first thing we did. So be able first to understand that there's the negative side and positive side to your graphs. But the most flexible graph that's out there is the velocity versus time graph. And it's the one that, I mean, it's one that was just on your practice test the other day. You know, be ready to describe what this does. It tends to still stump students, right? This is the graph of an object thrown up into the air, right? I know that because this is the part where it's traveling upwards, positive displacement. This is the part where it's traveling downwards. It's the negative displacement. This is when the object reached the highest point. All of those are things you should be able to determine from this graph. And it should be second nature. But I know there's people who think that the arrow is pointing to when the object is at the origin. I know you're there. You got to get away from that. This is not telling you where the ball is. It never does. It tells you how far the ball has moved. This could be a guy, you know, underground throwing the ball upwards. I don't know where the ball is. On the other hand, a more likely graph, and this has actually been on the multiple choice section of the exam, is to give force as a function of time. So something like this. And ask you how fast an object is going at the end of an interval. So I'm going to put some numbers to this just to give us something to do. All right, so all right, we're going to assume we're starting from rest. And I would like to know, what's the acceleration at 4 seconds and how fast is it going at 4 seconds? First, question A is not meant to distract, but it's meant to screw over the kids who aren't really paying attention. They'll get A right often because you've got force, 20 newtons, mass, 2 kilograms. You can F equals ma and get to the acceleration is 10 meters per second squared. Everybody follow that so far? So that's usually what people will do. They'll get this one right, put the 20 there, 2a, a equals 10 meters per second squared. And then the next thing they're going to do is say, okay, initial velocity was 0. Time is 4 seconds. I can figure out final velocity. And that's 100% wrong. But when we do this, we'll get 40 meters per second. And I guarantee that's an answer that's going to be an answer choice. The reason students screw this up is they forget you can only use VF equals AT plus VI if the acceleration is constant. Does this object have a constant acceleration? Looks to me like it doesn't. The force is getting greater all the time. So the acceleration is getting greater all the time. Now you understand they're setting you up to make this mistake. You have to understand that this is a force versus time graph. The area under it is impulse. Force times time. Which means the area under this is the change in momentum. So to get question B right, you have to do force times time, which is 1/2. So you have to do the area, which is a triangle. So 1/2 base times height, which looks to be 40 kilograms meters per second. And that equals the change in momentum. So I'll get 40 equals 2v final minus 2 times v initial, which was 0. So my final velocity is 20 meters per second. See, the thing about the AP exam is it's not just them they're not trying to trick you, but they are trying to see if you're not thinking it through. And if you're presented with a graph, they went through the trouble of making a graph. It's not incidental, especially if they ask more than one question about the graph. That should send up warning bells right away. they ask 2 questions off of a graph, especially if one of them seems super straightforward, like what was the acceleration, be very careful of the next question. They don't put pictures on the physics test haphazardly. They're careful, and the pictures themselves have been carefully selected, just like the problems themselves. A physics teacher wrote this, so they're looking for something specific about physics. That question was, they have thousands of questions to choose from, so they don't pick them arbitrarily. They've been working on this test for 6 months. It's not like me who works on a test for, a day. That's why my tests aren't as good. These tests, 6 months, a team of people has been sitting there going over this test, getting it ready for next week. Every item chosen on it was chosen specifically for a reason. So be aware, there are easy questions, middle questions, and hard questions. And this question itself wasn't hard, but I bet a lot of students will miss it. Well, how about this? This was on an exam. This was on the AP, the original AP exam, except question B wasn't what the velocity was after 4 seconds. Question B was, what was the kinetic energy after 4 seconds? That's a lot. Not only did you have to find the velocity, but then you had to go back and calculate the kinetic energy. There's no other way to do it but this way. No shortcut. Now, talking about analyzing graphs, all I have to do is change this a little bit, and the graph is a different animal. So if I put this as position, force as a function of position. Believe it or not, this is the graph of a spring now. Remember, a spring is F equals Kx. The slope of this line is K. And since it's a force as a function of position graph, the area under this graph is energy or work. I could say, what is the change in kinetic energy from this one? You could get it directly by looking at the area under the graph. You want me to talk more about graphs? Look at that table that I gave you on that summation sheet, the one that has like all the stuff about physics all in one place. The table at the bottom tells you everything I think you need to know about graphs and what they can't tell you. So, and you guys from Monsters class, I'll attach that here. I'm not sure if it's helpful at this point. We're getting pretty late, but it's got some stuff on it. So I'll look at it at the end. I don't want to spend time looking for it now. So it's bound to be somewhere. Let's see, what else? We are running shorter on time. So rotational torque or collisions. Let's handle collisions real quick. All right, we can do rotational torque. We got 20 minutes, so I can do both. And I'm not sure what you mean by rotational torque. So a lot of students had difficulty with the FRQ I gave that had the hooks in it and the weights. You guys remember that? So just for a little bit of redemption here, if I have something that's just a uniform bar and I try to get it to balance, and I place this pivot point, say, a third of the way in, it won't balance. Right now, there's an unbalanced torque acting on the system because the bar itself has a center of mass at the middle. Now, there's actually lots of ways you can kind of consider this. Some people have a hard time with the whole thing of center of mass. If you don't like dealing with the center of mass, you can break your bar up in the middle. and say that you have one thing pulling down on this side and another thing pulling down on that side, if that makes you feel better. But that's not how I teach it. But that's really what's happening. Some of the mass is on the left side of the pivot and some of the mass is on the right side of the pivot. Gravity acts on the whole bar. It's just that mathematically, you can treat it like all the mass is right there. So that's why we do it this way. But this would be in the middle, 1/2 L. So the torque arm is from here to here, this value. That's the torque arm. So if I wanted to find out what the net torque is, like I'll remind you, there are kind of 3 buckets when dealing with torque. Oh, thank you, Anaya, for posting that. That was great. So the first bucket is the torque arm length. The second bucket is the force, and the last bucket is the angle. So for a problem like this, it's nice, the angle is 90 degrees. The force is going to be the weight. You're going to have to do a little work to get the torque arm length. It happens to be, 1/2 L minus 1/3 L. That's going to give you the torque arm length. Because we want just the distance between where that pivot point is. That's 1/6 L. But that part's not the hard part. The hard part is that this system has an unbalanced torque now, which has to equal I alpha. If you want to balance it, would you put a weight on the A side of the bar or the B side of the bar? You want to get it to come to rest. There's nothing you can do with a weight on the B side of the bar that's going to help this come to rest. The only place you can place a weight would be on the A side of the bar. And you'd have to place something that's of equal torque. So whatever mass you have to place it in such a place where it provides an equal but opposite torque. Now, that means either picking the right size mass and placing it appropriately, or if you only have a fixed mass, finding where you can place it over here that will cause a balance for that torque. Now, the problem we had talked about, a variety of things, like what would make the acceleration greater. Well, you'd hang something over here if you wanted to make the acceleration greater. That would certainly add the most possible torque. You want to make it the least? Well, you'd hang something over here to make it the least. That would cancel out the most possible torque. Now, I want to talk about something else too here. We tend to get bogged down in sometimes other details of a problem that I think get us off track. If I tell you that I have a merry-go-round that's at rest and a kid runs and jumps on it, when the kid runs and jumps on it, this is a collision. It's a rotational collision. So it's not a linear collision, but it's still a collision. When the kid jumps on it, the whole system's going to be rotating now after the collision. What we tend to do is we talk about the before case and the after case. Before he jumps on it, it's just him running. After he jumps on it, the whole system's rotating. But there was a torque applied to him, and there was a torque applied to the merry-go-round. It occurred during the time interval, which is probably very short, when he was stepping onto the merry-go-round and the merry-go-round began to move. This might only lasted a fraction of a second, but during that time, there was certainly an unbalanced torque. There had to be. There had to be an unbalanced torque because the merry-go-round's velocity changed. And that's a sign to me that there had to be an unbalanced torque. I don't have to know what that torque is to know that the velocity now is different than it was before. But remember, this AP Physics 1, a lot of times it's just about describing how you know something happened. Anytime an object has a change in velocity, there is an unbalanced force. Newton's second law applies. Now, there are specifics. I could, figure out that there's a torque arm length of R here, and he probably pushed on the platform with some applied force, probably friction from his feet on the edge of it, or him grabbing the bar or something. And maybe I could use that to figure out how fast it's going now. But I also know that this is a collision. And because it's a collision, I can look at the angular momentum of the child before, lowercase l, point mass, angular momentum, and the angular momentum of the system afterwards, uppercase L, a single object that rotates about a fixed point of reference. Now, the specifics of this are more complicated. We know this is I times omega, and that I has got to be the moment of inertia of the merry-go-round plus the moment of inertia of the child, all times omega. The hard part is remembering that the child has angular momentum too. Even though he's not rotating, we kind of think of him as rotating as he runs along this path and jumps on the merry-go-round. It's been a long time since we talked about it, but you'll recall I said that this is R perpendicular mass of the child times their running velocity. So this was the last topic we had before we went to simple harmonic motion. So this is like in February. This R perpendicular, it's the same as the radius of the merry-go-round because they jumped on the radius. But it's a collision. The angular momentum was conserved. His jump onto the merry-go-round doesn't cause an unbalanced torque on the system. It applies a torque to the merry-go-round and a torque to him. They are equal and opposite. Now, just so you know, the linear momentum isn't conserved because the merry-go-round is fixed in place by a pivot point. So the kid loses linear momentum. There's an external force. Which brings us to a little bit, more base collisions. We tended to focus our collisions on linear momentum because they were easier to see, easier to imagine. So you have the before and afters of collisions. All collisions have kind of a before case and then some kind of after case. The thing I try to make sure we always consider about collisions is that no matter what happens in a collision, we tend to not think about the during case. We should be considerate of the during case, but we tend to not think of it. The during is when the forces are being applied. There are impulses during a collision. Cart 1 experiences an impulse, and cart 2 experiences an impulse. There is a change in momentum of cart 1, and there's a change in momentum of cart 2. However, the net change in momentum is 0. It's a collision. So if I have a 5m car traveling at 2 meters per second to the left, and a 2m car traveling at 3 meters per second to the right, and I'd like to know how fast the cars are going after the collision. And I don't know which way they're going after the collision. They could be going left, they could be going right. We don't know the answer until we figure it out. The mistake students are going to make here is momentum has direction. You had better determine a direction that you will call positive before you start the problem. So I'm going to make this way positive. Okay. So that means, looks to me like 2 times +3 momentum of the first cart plus 5 times -2, the momentum of the second cart. That has to equal 2 plus 5 times their final velocity. So I get 6 minus 10 equals 7 VF. So it looks like the final velocity is -4/7 meters per second. That clearly tells me that it's going to the left after the collision. Now, we kind of knew that, right? The bigger car going to the left had more momentum than the smaller car going to the right. Now, you need to be careful because I don't think we're looking at this as on the exam. I think we see questions more like this on the exam. You see kind of what I'm drawing here? This is a problem that has a collision in it, sure, but that's not the whole thing that happens. There's the collision, but then there's what the spring does next. And that's that middle thing. And that's why we try to remind you guys that don't forget that things happen in stages. There's the instant before the collision, and then there's the instant after the collision. It's important to distinguish that this problem has conservation of momentum, where the arrow hits the block and causes the arrow block system to move. And then there's the time after the collision, where the block is acted on by the spring, where energy is conserved. We mix up the fact that energy isn't conserved in the collision and momentum isn't conserved when the block acts on the spring. We have to compartmentalize when we can apply one law versus the other. So there's the mv of the arrow equaling m plus mv for the arrow and block together. That's the collision part. The instantaneous moment before impact and the instantaneous moment after impact. But then there's the kinetic energy of the block and arrow together. And we can set that equal to the elastic potential energy stored in the spring when the system is brought to rest. So conservation of energy occurs in one portion of this and conservation of momentum in another portion. It's incumbent upon you to be able to determine which is used when. Does that make some sense? I usually think it's pretty easy to kind of set up when one happens and when the other one happens. Just be aware that collisions happen very fast. They are instantaneous, is the way we kind of look at them. They're happening quickly. So we only consider the moment before and the moment after. Because you guys understand that this problem is the same as the dart striking the pendulum and the pendulum block swinging upwards. Those are the same question. It's just that I'm replacing gravitational potential energy with elastic potential energy here. Okay, that is 2 hours of physics. I'm looking at the body language, and Rachel's making that perfectly clear. But I think we probably should wrap this up anyways. We've gone through a lot. And look, I think you guys are very, very well prepared for the exam. But if you have follow-up questions, send them to me. I'll send back follow-up answers. I did something on purpose. I did all of this out on my porch with my batteries so that I knew I would run out of batteries in 2 hours. And I have 5% battery left on my computer. So no matter what, I have a forced end time. And I did that to myself on purpose because otherwise I sit and just chat. And you guys don't need that. It's a beautiful Saturday and you should go enjoy some of it. So is there any follow-up question that you want to ask real quick before I sign out?
Will you, sorry,
You can
Go
go.
ahead.
where will you upload this recording?
Let me pause the recording. So there's lots of variations to this question. So let me just be really clear. The slab sliding underneath a falling rock has really been trod a lot of ground in the old physics environment. So it's something like this, where you have this big block, say, I'm not very imaginative for numbers right now. And this block falls on top of it. So the 2 kilogram block falls on top of it. The whole idea here, this is actually just another version of a conservation of linear momentum question. And it is a perfectly inelastic collision. Our expectation is that after the collision occurs, there will be a 2-block system, but that they will both have the same velocity. We don't assume that any downwards velocity here contributes at all to this collision because that's completely absorbed by the ground. So we treat this collision as if we would treat any other collision where 2 objects stick together, and that we'd have 5 times 2 as our initial momentum, but then 5 plus 2 for the masculine block times V final as what we get for our final momentum. So the final velocity in this case would be 10�7 meters per second. Now, they spice this up by adding it to a spring. We saw that once. So just be aware, because of the limits of what you guys know, they can drop the block only 2 different places. They can drop it when we are at, hold on. We can drop it when we're at Vmax. If they drop it at Vmax, it's this collision problem where the velocity instantaneously changes to something less. In that, if they're doing that on the exam, you're having to deal with the simple harmonic motion and the collision at the same time. So if they do that, V is going to go down. It's going to get slower, which means the kinetic energy decreases and the amplitude decreases. But also the mass increases. So the period increases. That's the simple harmonic motion part. Now, the other time they do this is when you're at the max displacement or when you're at the amplitude. They can drop the box then. However, the box isn't moving. It's not a real collision. When they do that, none of this is true. Just this changes. The energy is the same because all the energy is in the form of elastic potential energy. And that doesn't matter. That's not based on the mass. So the mass increases, the period suddenly increases. The Vmax will go down, but not by the same amount. It'll be different. So I don't know who asked about that, but how was that for a quick response?
That's good. Thank you.
You're welcome. All right, folks, I'm going to end that here. And